Okay, so the stage is yours, Ohad.
Cool. Can you see my screen?
Yeah. Yeah, we can
Awesome.
see your screen.
Cool. Yeah, so I guess just some quick background before I kind of get into things. So I guess first of all, my name is Ohad. This is like some research that I uh, was doing, I guess for the past couple of years now, and I had the opportunity to present it at a conference over the summer. So I think this stuff is a little bit like out of my mind now. Like I haven't thought about it in a while, so hopefully I can like remember all the context and stuff. This probably isn't as smooth as it was a few months ago. But I guess feel free to interrupt and ask any questions if I'm like doing a terrible job at explaining something. So yeah, I guess with that, here is the presentation. So I guess I'll just say the title real quick as well. So this is called Linear Promises Towards Safer Concurrent Programming. And the idea here is that we have this idea of concurrency in programming, right? And this is basically the idea that you can have multiple things occurring at the same time. So for example, it's like the reason why you can go download a file and keep interacting with your computer as it's downloading. And this is really nice, but it's also hard to reason about because like kind of it's in the name, I guess. Like you have multiple things happening at the same time, and it's hard to predict like the order that things will happen or how they might interact with each other. Um, and so in practice, just trying to coordinate all these threads to do things that you want them to do is often very buggy, and it might lead to things like deadlocks or race conditions and all sorts of stuff like that. So people are pretty smart, and programmers have come up with a bunch of different solutions for this. So one of the like really like foundational solutions in the kind of space that I'm exploring is the future. And the idea of futures is that um, they allow you to basically communicate between threads in a way that one thread basically goes and runs some long task asynchronously, and then the other thread waits on its result. So in this diagram, right, like thread A can be doing some big computation, and as soon as it's done, it's going to yield that back to thread B, which is, I guess, waiting for the result of A. So this might be like downloading a file. You can schedule that off in the background in a new thread, and then as soon as that's done, you can start doing actions on that file. Um, these are really high level, and that's nice because it means that they're easy to think about, and it's hard to create a lot of types of bugs when you have high level primitives. But at the same time, they're not really general. So for example, you can't take like uh, you can't like go ask a thread to download a file and then have that like do something else and hand over the responsibility to another thread to fulfill. Or like another thing is like you can't have it fulfill multiple different futures, right? Like you can't say like this thread is going to download files A and B and give A to thread A and B to thread B. I don't know if I'm explaining that well, but essentially like this diagram is like all you can do with futures, right? You can't have like multiple nodes branching off. So a higher level kind of generalization of this is the promise. And so the way that the promise works is that it's essentially a future, but it gives you the capability of like passing around the ability to write to the promise or to fulfill it. So in this diagram, right, you have thread A has two promises, right? It has a promise to thread B and a promise to thread C, and it can fulfill both of those in any order at any time. Um, and likewise, if it wanted to, it could take the this promise that it owns and pass it to another thread to fulfill instead. So like I said, these are more general, but being more general, that means that there's more bugs that are possible. And so I'm going to talk a little bit about what some of these bugs are and how we can kind of approach fixing those. So the first bug that we kind of identify is what we call the omitted write. And the idea here is, say you have a thread A and a thread B, and A has like a promise to thread B that it's going to create some value. We can just say it's like downloading a file, for example. Um, but you can have a bug where thread A never actually fulfills the promise. So for example, like maybe there's an error somewhere, and so it just doesn't tell thread B that anything happened. And what happens in effect here is that thread B is just left kind of hanging forever because it never receives the result that it's expecting. And this can lead to all kinds of bugs. Like it has many of the same effects as deadlocks, even though it's not really a proper deadlock. Um, so I'm just going to go through kind of an example of what this code might look like that would cause this in C++. So again, feel free to interrupt if y'all want me to explain the syntax in more detail. But for example, let's say that we have a promise called sender, and this is going to contain an integer. And then we have the future called receiver that's associated with that. So for some like C++ background, the promise is the person who fulfills, and the future is the person who waits on the value. And so this is how you would create kind of this like link of like the promise and the future. Um, and what we're going to do is we're going to say that like there's this condition that never happens to set the value of the promise. And then after that, we're going to wait for the value of the promise and print out its value. But what's going to happen here is that because we never provide a value to the sender, then the receiver is never actually going to get anything. This line, like line 7, is just going to block forever, and the program will never finish executing. So I think another like related bug here is what's called the double write. So the idea here is, let's say we have a promise from thread A to thread B, and instead of like forgetting to fulfill it or fulfilling it once, thread A fulfills that same promise twice. So this doesn't seem like too scary when you think about it at first, but what happens is that there's now two values that might belong to this promise. And it's really like unclear what the correct value is. So for example, you could just say that the most recent value is the correct value, but then you introduce a race condition because the first value that you produce is now like being read in one spot, and the second value produced is being read in another spot. And you don't know, like, based on the order in which the write and the read happen, the results of the program would change. And likewise, like if you were to always use the first value or the last value that was provided, then you would create like some confusing semantics because you could like create a result and just lose it based on when writes happen. Like for example, you could say like, I'm done downloading this file, and then someone else says, I'm done downloading this other file, and the results of the first one will be overwritten. And so like nobody will ever see that you finished writing that or reading that file. So let's look at the code for this real quick. So like before, we can create our promise of an integer called sender, and then we can create the future for it called receiver. And this time what we're going to do is we're going to conditionally set its value, and then we're going to unconditionally set its value. And so the idea here is like this is how a double write might happen in practice, right? Like you might have a condition where you set the value, and in another place you're setting it, assuming that it wasn't already set. So you could get rid of this if true, and it would still be a double write, but this is just to kind of show how it might happen by accident. Sorry. And like I said before, right, like it's kind of like unclear what to do when this happens. In C++, this is going to result in an exception, but other languages will do like other weird, quirky things. And so it's a little scary to have this because like it's almost like undefined behavior in some ways. So the third kind of bug that we identify is the unowned write. And this is really like very closely related to the double write, but it's like a little bit weirder. So the idea here is that you have like a thread A that has a promise to a thread B, and then the thread C also has access to that same promise. And basically this is the type of bug that occurs where thread A thinks that it owns the promise and has the responsibility to fulfill it, but thread C kind of beats it and does it first. And so like before, this is scary because it can create a double write, but it's also just like a really confusing case to think about. In general, like it's scary to have multiple threads with the kind of like ability to fulfill the same promise. So just to kind of show you what this might look like, like before, we're going to create our promise and the future for it. And now let's say that we have another function that runs asynchronously called f, and we're going to give it this sender. And behind the scenes, it's going to go ahead and fulfill that promise. But then on our end, we're also going to want to fulfill it as well. And so this is like scary because we can't really look at this code and know for sure whether there's going to be a double write. And also, it's just like, even if we could make this code, like even if we knew that the function f said like, if not something, then set value, the condition of this something function could like change in between. And so it's just like scary having this kind of access in multiple places. There's very few cases where it doesn't feel like a bug, I think. So yeah, I think that's about it for the three types of bugs that we're going to talk about. But if y'all have any questions about those, feel free to interrupt. They might kind of come up again later. Yeah, so the next section about this is basically our approach for a solution. So the idea here is what we call promise ownership. And so, like, let's say that we could take this kind of notion of promises, but we'll kind of extend it with one extra piece, which is the fact that a promise has an owner, right? So this is the promise, and this arrow is saying that the function A, or sorry, the thread A owns this promise. And what we mean by owning a promise is that it must fulfill that promise exactly once. So for example, if thread A is the owner of the promise, then thread C can't come out of nowhere and write to it. And likewise, thread A can't double write or can't forget to write to that promise. And if we can't fulfill it in this thread, what we're allowed to do is transfer it exactly once to another thread. So for example, if thread A decided that it's done executing, but it still needs to fulfill this promise, then it can spawn a new thread C and give it the promise. And now C is considered the owner of that promise. And so the advantage here is that we can get rid of the omitted write bug, right? Because there's no situation where a thread can terminate without fulfilling its promises. We can also get rid of the double write for a similar reason. It can't terminate, or it can't write to the same promise multiple times. And like I said before, there's also no unowned writes here. So if we can implement this kind of ownership model, we can sidestep all of those bugs that we discussed earlier. So how is this possible? So the way that we approach this is by doing basically some extensions to a language in the type system. And so the way that this looks is that we have what are called linear types. So linear types are basically a way of saying that there are values that can only be used exactly one time. And this is pretty similar to like how Rust works behind the scenes if y'all are interested. I can talk a little bit more about that. But the idea here is like whenever we have a linear variable, you can't get away with just like forgetting to use it, and you can't use it multiple times. And if we kind of use that notion, then we can implement a lot of the same guarantees for promises. So as an example of what a linear type system looks like, let's say we have this variable x, and this is just an integer. But if it's a linear variable, it'll be an error if we try to print x plus x, because in this expression, we're using the linear variable twice, which is just not allowed at the type system level. And likewise, like let's say we had this variable y. If we just returned without ever doing anything with the variable y, then this is also going to be an error. So in this case, like integers are like a weird kind of thing to make linear, but this is kind of the notion that we're going to extend to work on promises. Yeah. So in a little bit more depth, the way that this kind of looks is that we can take the promises and break up their responsibilities. So earlier we talked about how there are there's like the promise object in C++ and the future object in C++. And the promise is the one that writes a value, and the future is the one that reads the value. So in our language, we use the syntax promise star of t, where t is like some type. So like you could have like a promise star of int, and that's the side of the promise that writes. And then there's also promise of t, or like promise of int, that is going to consume the value inside of the promise. And by doing this, we can make it so that like the write end, or like the promise star, is linear, meaning that you can only write something once using the write end, but you can read it as many times as you want. Cool. So the kind of background for a lot of this stuff is based in a paper from another grad student at GT. And this paper is basically on the idea of promise ownership, but at runtime. And the kind of idea that they came up with is that you can dynamically detect all deadlocks if you know that all promises are fulfilled and there are no kind of like dependency cycles in those promises. And the interesting thing here is that the way that their language worked is that it relied on promise ownership, but it required like the user to annotate the program with things saying like who owns what. And because we're inferring all this at compile time, we're actually able to kind of retrofit our type system onto this research to allow for basically like less overhead for the programmer while having like dynamic deadlock detection as well. Cool. So in terms of like the actual language and how it works, These details aren't like super important, but this is just kind of to help you read some of the code in the later slides. So there's like a few different examples of what the code might look like here. So the first line shows you how a variable is defined. So this defines the variable to have the value 0, and its type is inferred. And over here you can just see what a comment looks like. We also have this syntax for creating promises. So you create the read end and the write end at the same time, and you give it a type. So for example, you could say like, I'm going to create a promise called sender and receiver, and it's going to have type foo. And then on line 3, you have an example of both a function call, which basically we just, say f, and in parentheses, you give it its arguments. But we also have some other things here. So async is a keyword that allows us to go run something in the background in a new thread. And this question mark operator allows us to wait for the result of a promise. So what line 3 is doing is it's going to wait until the read end of the promise resolves, call a function with that value, and do all of that in another thread. And so we can just continue straight down to line 4, and this is just showing us how we can fulfill the value of the write end. So what's going to happen here, right, is because line 3 is asynchronous, this thing gets scheduled in the background, and we move straight to line 4. Line 4 fulfills the promise, and then line 3 receives the value and can continue executing. So as a kind of quick example of some code, we're going to create a promise with a receiver and a sender, and this promise is going to contain a string. And we can initialize that with the string hello world. And now we're going to print out the result of waiting for the promise. So this is just going to run and immediately print out hello world because there's nothing asynchronous happening. But if we were to actually remove the line that fulfills things, then in our language, this program wouldn't compile because the sender variable goes unused, even though it's a linear variable, which our type system defines to be an error. And likewise, let's say we go back to this original program, but we insert another fulfill operation right here. So now because we're fulfilling the same linear variable twice, this is also going to be a type error, so the program won't compile. And the reason here is that we're using a linear variable multiple times, which is sender. And as you'll notice, this is the past slide was a omitted write bug, and this slide is a double write bug, but neither of those are actually possible to express in our language. And then finally, in terms of the unowned write bug, let's say we were to pass the sender variable to a new function f, which would become the owner of that. This is pretty similar because we're reusing the same linear variable twice, which again is going to be a bug here. A type error here. So this program won't compile. And that's kind of the way that we're able to avoid compiling programs with unowned writes. Cool. So this section is pretty kind of in the weeds about how the type system and semantics are implemented. So if y'all are not super interested in this, I'm happy to kind of skip over it. But I'm going to try to kind of quickly gloss over some of the details and see how much I can kind of get across of the core ideas. Right. So the way that we kind of think about a lot of these things in terms of programming language theory is we want to describe the language as two different things, which is number one, what happens at compile time, and number two, what happens at runtime. And so the runtime semantics allow us to basically say how a program runs. And so for the sake of this, we're going to define the program in terms of threads, where a thread is composed of a thread ID and its expression, which is the thing that's currently executing in that thread. And we can also create these trees of threads so that basically a binary tree of all the different threads that are currently executing. And these are all running in parallel, basically. And so what we can do is we can actually describe the entire state of the program as this tuple, where we're going to store its next ID that's available for the next thread. We're going to store a map of all the promises to their values, a map of all the promises to their owners, and then finally the tree of all the threads. So this isn't super important, but this is just all this state that you're going to kind of be seeing in the next couple slides. So this is just going to kind of guide us through how a simple program might run. So what you have here is kind of like the empty program state, and this uh, syntax highlighted part is like the actual program that's running. And so we're going to start out on like line 1 here by kind of running this promise construction code. And so what we're going to do is we're going to add these kind of variables into the scope. So we have our message is the receiving end, and then we have send message is the writing end. So this is like a promise and a promise star, and they're both going to contain strings. And then we're also going to add this promise as an unresolved promise to the promise values map. And we're going to say that thread number 0, which is this thread, is the owner of this promise number 1. And then we can just increment that ID. That doesn't really matter. And we're done executing that line. So on the second line, what's happening here is we're going to run this stuff asynchronously. So this is like basically telling us that everything on this line is going to happen in another thread, which is like a fork operation. So we actually split this up into 2 different threads now. So now we have thread 2 that's executing the print from the previous line. And we also continue on the next line, which is the send message in the current thread. And so here, what you'll notice is that the second thread is actually going to be blocked because message is currently unfulfilled. So instead, we have to execute the first thread. And what that looks like is it's giving us a value to resolve the promise to. So we can kind of update this promise values map. And then we're able to unblock the next line because now the promise has a value. So we're able to just read that value in and then go ahead and print it, and the program is done. Yeah, so that part is like probably not super interesting, just kind of like details of how stuff works. These next couple slides are kind of similar, but this is just kind of going over how we implement the type system. And so like I said before, we have linear types, which means that basically like a linear variable can only be used exactly once. And so the way that this kind of works is we have to determine what variables are linear. And those are all variables that are promise stars or contain a promise star. So for example, if you have like a struct that has a promise star in it, then the struct is also going to be linear. And that means that you can only use that struct exactly once. And so these are just some rules that kind of like describe how this linearity functions. And just to kind of give you like a high level idea of what's happening is at any point in the program, we're going to split it up into like multiple environments of where an environment is basically like a set of all variables in scope. And so we will say that only one of those environments will contain any given linear variable, which means that if you have like 3 lines of code in a row, then only one of those lines can actually use the linear variable, and it's not in scope for the rest of them. And an important piece here is what's called weakening, which is basically being able to say that we don't use this variable, so we can remove it from the scope. And you'll notice that this only works for variables that are not linear. Whenever there's like a linear variable, we're not actually able to remove it from the scope. Cool. So this is just kind of going over how the product rule works. So like I said before, we have this notion of splitting the environment, which is gamma 1 and gamma 2. And what this means is like, let's say we have this line of code right here, which is just like constructing a tuple where it has an expression 1 and an expression 2. We'll say that gamma 1 is assigned to E1 and gamma 2 is assigned to E2. So that means that like any linear variable is only going to be in gamma 1 or in gamma 2, and by extension, it's only going to be either in the left variable or the right variable that's constructing this tuple. So yeah, that's about it for like the kind of formalisms. Just some quick high-level things about the implementation is that we kind of like generalize this language to actually be useful. So it has loops and IO and recursive types and a decidable and efficient type checker, which is, I guess, pretty useful. Here's some stuff about how fast it runs. And yeah, I'll just kind of go into the results. So the interesting thing here is that we basically have shown that promises can be made to be as safe as futures. And this is kind of true in the sense that futures do not allow double writes or unowned writes. And if we use normal promises, those are possible, but once we add this notion of ownership, we can make those impossible again. And at the same time, we can also say that as long as a program terminates, there's not going to be any omitted writes. So the exception here is like if you were to run an infinite loop, you could kind of get away with like never actually fulfilling a promise. Um, but what's true about this is that this is like the entire kind of safety gap between what promises and futures can do, right? Because uh, all of these bugs are impossible with futures, with like, again, the exception of like an infinite loop with a future can still cause you to never fulfill a promise, or sorry, the future. Um, but at the same time, we actually have like this extra kind of generalization of what futures are able to do using promises. Um, so here's just like a kind of fancy table showing like the capabilities. So I think like in some ways, you kind of get the best of both worlds using these own promises, with like some trade-off of being harder to write programs with them. And then kind of like a final piece here is that this actually works in practice. So the idea here is we did some work kind of building on this previous case study of JavaScript programs. And they had kind of categorized different types of bugs related to promises. And what we showed is that the type checker was actually able to detect the same bugs that they had kind of like manually detected in their case study. Um, and in fact, like we only expected it to catch a few of the bugs, but it was able to catch like almost all of them. And the reason there was just that the like normal kind of type system guarantees of like a statically typed language are actually able to catch just a huge amount of the bugs that you might see in like a JavaScript program. Um, yeah, so that is about it. Obviously, there's a lot of details in the paper, and I'm happy to answer any questions that kind of go into depth on stuff if y'all are interested. But otherwise, anyone have any questions?
Yeah, thank you so much for presenting. I had a question about the thread scheduling. So, how
Hmm.
does the runtime decide which thread to run?
Sure. Yeah, so I can go back to I think it's on this slide, I guess, is kind of like how it works. So I guess like part of the interesting thing about how we talk about like the runtime semantics of a programming language in terms of like programming language theory, is that we don't actually like care too much about the details that um, like I guess like how scheduling might work. Um, what we do know is like in this case, like this thread is blocked, so it can't run. But let's say like that this wasn't a blocked thread. We actually want the semantics to say that any thread can run at any time. And the kind of reason for that is that there's like this non-deterministic aspect of um, parallel programs. And that's actually like something that is implicitly like a part of the model of the language. Because if we have like non-deterministic ordering, then that means that like race conditions are possible. And if we were to have like a kind of deterministic scheduling algorithm, that wouldn't really be the case anymore. So I guess like it doesn't really describe that, but I think it leads to like some interesting results because uh, it means that we can be a little bit more general in our proofs and stuff like that. Does that kind of make sense?
Yeah, that makes sense. Thank you.
Hmm. And I guess I should kind of preface that with like the fact that I am not an expert on programming language theory by any means. So there's totally a chance that like that might be true for like this one paper and not true generally speaking. But yeah, that's basically like as far as I'm aware, kind of the general practice.
Do you mind explaining how to read some of the like the type theory stuff,
Yeah,
like
sure.
the
Uh,
inference rules, basically? Yeah.
mhm. Yeah, so let me just jump ahead. So I think this slide is like a really good one to start with because these are really simple inference rules. So for anyone who hasn't seen an inference rule before, basically an inference rule is like one of these kind of like fraction looking things where you have like a line and you have some things above it and some things below it. And the idea is that the thing on the bottom is like your conclusion and the thing on the top are like the conditions for that conclusion. Um, so it's almost like kind of like an if like the top thing is true, then the bottom thing is true. And this is basically just like how we would write a lot of these kind of like type system rules or a lot of these semantic rules to kind of like describe what the system is doing at any particular point. So in this case, like this first rule is saying that the thing on the bottom is unconditionally true, which is that promise stars with any type T are linear. Um, and so like I said before, right, like the idea of this type system is that anything that's a promise star, which again is like the kind of right end of a promise, is a value that you can only use one time. Um, and this is like how we accomplish that. And then likewise, like we can say that any value containing a promise star or another like linear value is also going to be linear. So what this line is saying here is that if we have a type T1 and a type T2, and T1 is linear or T2 is linear, then the product of those is also linear. So this is basically saying like if you have a struct with like a variable T1 in it and then another variable T2, if either T1 or T2 is linear, then the entire struct is going to be linear. And the thing on the right here is just saying the same kind of condition for like a union of two types, or like an enum, for example. So that's kind of like the basic way to read like the kind of like simple inference rules. But in terms of like what the kind of type system inference rules look like, here is kind of like uh, a little bit more complicated rules. I'm going to focus on this one, I guess. Um, so what's important to like kind of be familiar with is just this notion of what gamma is. And so when we have like type system rules, we say that gamma is the kind of like environment of all variables. So what it looks like is it's literally a list of like these kinds of type judgments, which says like, for example, X has type T. And so gamma could be like X has type T, Y has type T prime, and Z has type like T1 plus T2, for example. And that's kind of like the scope of the program, where everything else can kind of be said about like the type system. Um, so I guess like here's a rule that kind of shows how we would use that. This operator here, I think is called like the turnstile, is basically just saying that like in the environment described on the left, the thing on the right is true. So what this is saying is like if we have this list of all variables, gamma 1, then we can say that E has type T1. This is like pretty abstract, so I don't know if I'm like doing a great job at explaining it. But like for example, if gamma 1 was really like saying like X has type T1, and then here it said like X has type T1 on the right side, that would basically be saying that like because we know that there is a variable called X with a type T1, then like the program X also has type T1. And then we can kind of like generalize this by building like a tree of different rules. So what's happening here is like these are trying to handle all the different cases. Like T weaken here, or like weakening, is like one of the many rules that allow us to take a program and transform it into like another program that we can create like typing judgments on. So like as an example, right, you might have like a rule for like the addition operator, and you might have a rule for like variables. So if you have like a variable x and a rule for the addition operator, then you can say like x plus x has this type because the addition operator works in this way, and because like variables in scope have like the integer type or something like that. Um, I guess like these slides are probably not the best example, but I'm happy to like share some kind of better resources or examples on Discord later on if that helps. Um, yeah, let me know if you want me to like re-explain any of those things because I think I did a pretty bad job there.
So like, what is the box symbol with the plus and
Mhm.
yeah?
Sure, yeah. So I guess like a lot of the kind of notation like that you're using is very like dependent on the research you're doing. And like everyone kind of invents their own notation. So this is like a kind of symbol that I found in like one or two other places. And it's just one way of kind of describing linear type systems. So the way that it works is like this box plus is basically like almost like a union of gamma 1 and gamma 2. Um, so again, like gamma 1 and gamma 2 are like environments of variables or like lists of variables and their types. The way that box plus works is like it's saying that there is an environment composed of all of the variables in gamma 1 and all of the variables in gamma 2 with the condition that like any linear variable can only appear in exactly one of gamma 1 or gamma 2. So for example, if you had uh, like a promise star called X in gamma 1 and in gamma 2, then there's no like union that you can create of those two. Does that kind of make sense? Like,
Yeah.
the idea here is that we're able to say like if something is true in like this big environment with all of these variables, then we can kind of break up the environment into pieces that are belonging to one expression and pieces that are belonging to the other expression. Um, I guess this is like the slide that actually defines how that operator works, right? Like if you were to read these judgments here, or like these inference rules, I guess, like these would basically describe what this operator is doing in some sense. I think it's like a pretty abstract idea though. Like a lot of this stuff is like, for reference, like when I was writing this paper, a huge part of writing a paper is just like reading papers. And when you get to like papers that define like their own notation, you might have to read like literally like 50 of these inference rules and like write down notes to make sure that you're like actually understanding them and like prove things to yourself as you're going. And like you're constantly like flipping back and forth trying to make sure that you understand their notation. So like this stuff like should not feel intuitive in some sense. Like it is definitely like confusing stuff. So I hope I didn't like confuse anyone too much with my kind of summary of a lot of these things. And I
Um,
guess just oh sorry, go ahead.
yeah, I had another question that's unrelated to this, so if you wanted to say
Hmm.
something.
Oh
Uh,
yeah, I was just gonna say that like if people have like questions about just like the research process in general, then I'm also like happy to answer those. Um,
yeah. My question was on the case study. So the
mhm.
case study was in JavaScript, right? I'm
Yeah.
remembering. So
Um,
did you like port the programs over to your language and then
mhm.
study the bugs, or how did that process go about?
Right, yeah. So the kind of way that that worked, it was like we took the JavaScript programs and then ported those over to stuff in our language. And this isn't like a great proxy because um, like ideally we would want to evaluate programs in our own language, but like the limitation is like we had to create a new language to make this type system possible, and so that means that we can't really like go and like have people write programs in it or like use existing programs. But like part of what this is trying to evaluate is like the idea of like let's say that we took like the TypeScript compiler and we extended it with these like linear promises. Would that actually be solving people's like real bugs? And so like the kind of conclusion here is like to some extent, yes, it would. But obviously there's like a trade-off between um, like having to kind of think a little bit harder as you write the program to make sure you're not triggering any of those compiler errors, um, and like being able to kind of make sure that those bugs don't exist at compile time. Any other questions? Um, oh, I think there might be some stuff in the chat. Yeah, I can definitely send a link to the paper on Discord. I guess um, I have to look that up real quick because like I don't have it on hand, but I'll send that like at the end of this presentation. Um,
I guess I'll ask this question for everyone here, but um, so during your undergrad research, what was the process like interacting with a PhD student and the faculty advisor, and how much knowledge did you know coming into this, and how much did you learn from them? Like, could you talk a little bit more about that?
yeah, sure. So I think like I'll kind of start with like what I knew going into it. I was like I want to say I was like super like Dunning-Kruger, if like anyone knows what that is. Like I think I had like a very vague idea of a lot of these concepts, and I thought that I was like more prepared for research than I actually was in a lot of ways. I guess like um, the kind of process took somewhere around like 2 years, I think, from start to finish on this paper, which I think is like abnormally long, but also like pretty normal for like undergrads. Um, but basically, like there was like a ton of learning throughout the process. So um, I basically like worked directly with like one PhD student who was like towards the end of his PhD, and he was like mentoring me pretty thoroughly on um, kind of like where to start on the research process, right? Like the first step is basically figuring out what you want to write a paper about, and what you want to explore. And then like throughout the process, you actually have to figure out like what is the actual like approach that we're going to use to solve this? What is the kind of like approach we're going to use to argue why this is like a good solution? And you kind of have to like figure out a lot of the existing research in that space. And so like throughout the process, I was like super unfamiliar with that, and I think that's something you can only really learn with like a lot of time and exposure. But it was like super helpful working with a grad student and like a professor who were in the field already, who like had a good idea of what research is like important and related and things like that. So I guess like most of my work like early on kind of just happened as like here are some ideas we can work on, here are some papers that you might want to read, and then gradually like as the kind of stuff progressed, we were having like weekly kind of research meetings to discuss like how can we like implement this in a new programming language, how can we make sure that this approach is like general, and there was just a lot of like back and forth kind of discussion, drawing things on a whiteboard and making sure that we're like thinking about proofs in the same way and things like that. And then like gradually again that kind of shifted as the paper was like coming closer to being done because there was just a ton of like mentorship that I needed in terms of like how to write a paper, how to edit a paper, how to respond to feedback, and things like that. Um, so I think it's like it's definitely like a really long and uh, like tiring process in some ways. But I think you learn like a massive amount just like you learn how to like read, how to kind of think about like research problems, how to evaluate research and things like that. So it was super useful, and I'm really glad that I went through it. Yeah, so the language is open source. So the implementation is like kind of gross. Research code tends to be a little gross, but it basically is like implementing the same ideas. And in the paper, there's like a specific section that talks a little bit about how the actual compiler works with respect to like how it kind of alters some of the rules in the type system. And so I think like the implementation section of the paper might be like a better place to kind of start out. Um, in terms of like the compiler itself, it's not really like a like full end-to-end compiler. A lot of it is sort of hacked together. It basically just generates like Java code and kind of lets Java deal with a lot of the like semantic side of things. Whereas like the compiler is basically just like a type system that like does some very minimal syntax transformations.
So this is a question about the implementation. When you're
hmm
given like a set of inference rules that describe a type system,
hmm
how do you go about approaching the implementation of it?
Sure,
Or
yeah. So yeah, I can come up with like a pretty good example of that, I think. So um, I think it's like not always a trivial thing to do, right? Because there's some things that we can describe like really well as kind of like what the output of an algorithm is without actually coming up with a good way of implementing it. Like I guess like it's a little bit kind of like the whole like P equals NP thing, right? Because like we can like say that something is like a valid output from this algorithm without really having an efficient way of computing it. Not exactly, but just kind of like an analogy of sorts. But I think like this kind of like box plus thing we were talking about before is like a pretty good example of that. Because if you look at like how a research paper would describe a linear type system, this is like a pretty conventional way of doing it, where we say like if these things are true for like some environment gamma 1 and gamma 2, then you can like do all this stuff with it. But like in practice, like a type system doesn't actually have um, any kind of like notion of these different environments when it's running. And so you kind of have to do this like process of looking at these inference rules and trying to kind of figure out like a good sort of like backward step, right? Like we know what the solution is and we know what the inputs are, but we need to figure out how to take the solution and convert it to like something we can use on the inputs, which is like pretty abstract. But if you'll notice, like here, we're doing all this stuff about like deciding which environment a variable should belong to. Um, and the idea here is like if we can do that like dynamically, like if we can say like loop through this environment and say like which expression kind of needs each one of these variables, then we're able to um, implement an algorithm for that. So like the way that it works is like you really have to kind of like squint at this and try to figure out like where is like the for loop happening here? Like where is like the actual like computation happening? And it's not always something that's like super easy to do because some of these rules can just not really be like expressed in like a super efficient algorithm. Um, but that is like part of the kind of type system design as well. Like there's a whole design space of like what is a good type system in terms of what can be like implemented. And that's kind of why like on which slide is it? On one of these slides, we mentioned like the efficiency of the type checker because like there are type systems that are really, really cool, but will probably be like NP complete or something and will never give you a result. Um, so I think there was a lot of times like in the kind of design process where like I had an idea for how to solve something with like a typing rule and had to kind of like uh, redesign that because it wasn't really a thing that could be expressed super well in an algorithm. Um, I don't know if that's like a great answer. I think like I could kind of go a little bit more in depth into like how I did it for this particular type system, but I don't know how like generalizable that would be. So, um, but if you're interested in like doing something like that, like if you have like a research paper that you want to convert into a working type system, I'm happy to kind of provide some guidance where I can.
Looks like someone sent a message in the
Oh,
chat.
yep. Um, yeah. So where is it again? Yeah, so there's a bullet point that mentions that it is like empirically somewhat of a linear algorithm. So the idea here is like the type checking algorithm basically was proportional to like the size of a function times the size of like the um, or like the number of variables in scope. Um, and so like the number of variables in scope here is like the size of gamma, and the size of the function is like the size of e, right? But in practice, like people don't write 1,000 line functions with thousands of variables in scope. They write like generally like long functions with a few variables or short functions with a lot of variables and not really anything else. So like basically like this is like the worst case that we're talking about. But in practice, like almost every program that you can like conceivably write is actually going to be more efficient than that. Um, so like an interesting kind of like side note here is like if you look at like the type inference algorithm that like OCaml and Haskell and a lot of other languages use, it's actually I think like exponential time in the worst case, but that worst case is like such a weird edge case that in practice it's like not even noticeable. Like the type systems are like super fast to run because um, like people in general don't write programs that are like super inefficient to type check. Um, and yeah, so the other question is why does that matter? So right. So I guess like it doesn't matter a whole lot. But like if you kind of think about it naively, right, like this gamma times e is sort of going to scale like um, quadratically, right? Because if you make this implicit assumption that like as a function grows in size, it also grows in number of variables, then you would expect this to really be like secretly like e squared time complexity, which is not like terrible, but it definitely sucks a lot if you have like a 10,000 line function because it's going to make your code like super slow to compile. So like again, it's not like super important, but I think it is a consideration that people make when implementing a particular type system. Like nobody wants their compiler to take 2 hours to run. Um, and I think like even in terms of like a programming language like Rust or something, that is like something that they definitely uh, thought about in some sense when designing the language. Right, yeah, Rust is not actually that bad. I think in C++, like you can actually bump into cases where like because of like the way that templating works and stuff, uh, it could actually take like hours to compile a program, which is like sort of type system related in some sense. So I think it is like a realistic thing to care about. But like you're right, I think like if this like random research paper said it was like e squared, it wouldn't matter too much.
We're getting close to 7, but I have one final question.
Hmm.
Um, so, where do you see this work going in the future? What sort of extensions or directions you feel other
Hmm.
people can take to improve upon your work or get it integrated into something?
Sure, yeah. So I think that's something I thought about a little bit. So there's a couple different things that come to mind. So the first one is on one of these slides. I mentioned like some previous work from my lab that was I can't find the slide right now. But the previous work was on like a dynamic deadlock detector, which is using like a lot of the same techniques. Um, and the idea is like promise ownership gives us the tools to like dynamically find deadlocks most of the time. I found it. But if we like kind of like read between the lines here, right, there's like some possibility that a lot of these dynamic checks can actually happen at compile time. So I think it's like not immediately obvious how to go about that because we have to like detect cycles in this like dependency tree. So like let's say like there's another arrow kind of pointing back from thread B to thread A. That's easy to see at runtime, but at compile time we don't know like what order threads would be spawned in and what function belongs to what thread. But I think if you could come up with like a good notion for that, you would actually be able to detect like deadlocks at compile time, which I think would be like a really cool thing to do with this type system. Um, and the other kind of direction is just, as I was hinting at, like it would be an interesting thing to integrate into like say like JavaScript or another kind of common programming language because there's a lot of potential to actually like catch real bugs if you were to do that. So the kind of work there would take the form of like figuring out like what kind of like language um, features haven't been translated yet to this type system and how we could go about doing that. So I think like there's a lot of interesting things we could kind of pull from like Rust's type system design, but it's like a little bit difficult to say like how would you translate say like a like hash map or something because like the kind of naive solution is like if a hash map contains like a single linear value, then the entire hash map is linear. And that means that like the second you like access something in the hash map, then you can never use that hash map again, which is like a little scary. So I think there's like some kind of like balancing act to be done there in terms of like how can we actually like come up with a good way of translating like existing programs and extending existing languages. But there is like a sort of like straightforward path to a lot of the simpler stuff there. Um, yeah, I agree. I think it would be cool to see in TypeScript. I tried to like evaluate that a little bit. I don't know how feasible it is just because like there's a lot of really complex features in TypeScript that might make it hard. But I think there's like definitely potential to extend like similar work in say like Java or Rust or something that might be a little bit easier than TypeScript. Um, Yeah, I guess if there's no other questions, thanks for attending, everyone. I feel like this is super boring, but if anyone's still interested, I'm happy to answer any more questions and share the paper and stuff like that.
Yeah, thank you so much, Ohad, for presenting. Yeah, I'm actually happy you went to an hour, so that's good. Um, yeah, I will post the recording as soon as it processes and it gets into my inbox. And yeah, that's all I had. So,
Cool. Yep. Yeah. I guess like if anyone else has like any other questions about like the research process and stuff like that too, like feel free to reach out on the Discord. I'm always happy to like answer questions or kind of give some guidance there. Because I know it's like a little bit scary to do, especially as an undergrad. Um, but yeah, thanks again for attending, everyone.
right, I'll see you guys next week. Bye.